All right, let's finish this up. So we got done essentially with the procedural part of the second to last question. We are coming up with a way that we could determine the final speed. We know that or at least we're assuming that the energy is conserved in this. I know it's a collision, and I know the objects are sticking together, but trust me when I say this, the fact that the spring does not have mass is very important, and that means that the energy can be conserved. When we have two objects sticking together after a collision, most of the time we've got two objects with mass, and if they stick together we say inelastic collision energy is not conserved. It is very important that the spring, at least I'm telling you that we are assuming it right now, does not have mass. We can conserve energy this way. So, initial energy before the car hits the spring, it's got all kinetic energy. Afterwards, once it has compressed the spring to its maximum compression, all that kinetic energy has been transferred to elastic potential energy. We know the equations for both of these. We know that if we change the mass, as long as we make sure the starting point is the same for each trial, the speed will be the same. That will be a constant. That is what we are trying to measure here. Speed will be a constant. Spring constant, it's a name, is a constant. If we change the mass, that will cause the compression distance, the maximum compression, to change. Okay? This actually says if we increase the mass, it should compress more. Kind of makes sense. So we are looking to determine. Let's look at this equation here. We're going to be changing m. That should be changing x, the amount of compression. Now, this looks like something we could graph because it is very, very similar. I'm going to erase this for some extra space here. This looks very similar to our old friend, the equation of a line, y equals mx, m times x, plus b. Let's take care of the easy stuff first. There's nothing getting added on here. There's no b term. B is 0. M is the variable we control. It is our independent variable. Very similar to our x variable. Okay? Make sure you keep this m straight from this m. This is a mass, this is the slope. X squared, the amount of compression squared, very similar to a y variable, and then it's a dependent variable. And it's over on this side of the equation. Which leaves, for our slope, v squared divided by k. So, what we need to do, once we have all this data, we simply say graph x squared versus m, and then we say the slope will equal v squared over k. So, since we know k from above, all we have to do is actually numerically find the slope, do a slope calculation, y2 minus y1 over x2 minus x1. So we find slope, and then solve for v. Very simple, okay? I say very simple, but it's a process. It is not something, it's not a fact to memorize. It's a process that you need to go through and go through and go through, and maybe the 7th or 8th time that we do this, you're kind of like, oh yeah, I would have predicted that we were going to do that, okay? Linearization is tough. Personally, I don't think that I knew how to linearize stuff in high school. I kind of found out on the fly in college, and I realized it was very useful. If you guys get out of this classroom knowing this sort of mathematical method or tool, you were in a much better place than I was when I was leaving school. Okay, so congratulations on that. I believe we have everything. I believe we've kind of taken care of everything that we have here. Okay, this is one way that we could check our value for the velocity. Okay, one way we could experimentally do this. It would be a great lab to do. I would love to do this lab. It would be very, very fun to try and see if we actually do get a similar result. So, I'm going to erase this. We're going to move on to the last question, which is also almost a carbon copy of a question that I saw one time on the AP exam. I cannot remember if it's a practice exam or an actual exam. If it's a practice exam, you guys will see it when you come in for review sessions. If it's an actual exam, well, then we might have actually done this question before. I can't really remember. But the last question says something to the following. When the spring is completely compressed with the cart attached to it, a block of the same mass as the cart is placed onto the cart. Describe any changes to the oscillation that occur because of this. Let me sketch you a real quick picture of what's happening. So here's our cart. It is compressing the spring. Normally the spring is longer than this, but it is at maximum compression. And at this point, a block with the same mass gets dropped onto it. And by dropped, I mean very gently placed, right at this perfect moment of maximum compression. Now this should change some things. Okay, this should really change some stuff that's going on. How would this affect the oscillation? Let's start with, the first equation that we used. Well, the first equation we used was we used the period of the spring's motion to figure out the spring constant. Let's think about that equation again. That equation was this. Period of the spring equals 2 pi times the square root of m over k. So this is a pretty obvious change. If you increase the mass of the thing that is oscillating, okay, if you increase the mass of the cart as it moves back and forth, then that should also increase the period. So maybe the first thing I say is that since this is true, again, I'm answering in bullet points. I'm pretty sure you can do that on the AP. If you want to write in paragraphs, that's fine too, as long as your writing makes sense and is connected. So since the period of the mass on the spring, since this is the equation for it, and m increases, the period must also increase. It doesn't double, it actually goes up by a factor of the square root of 2, but it does increase. Okay? It's pretty easy to see why it should increase. Okay, so if the period increases, what this implies is that the system is not going to move as fast. Let's see if that actually ends up being true. If you are just placing another block on top of this cart, are you really adding any extra energy to the system? No, you're not. And you're actually not taking energy away either, okay? It actually turns out if you put this, I believe I did a problem once, if you put this somewhere else, then the energy of the system changes. Like if you were to drop the mass, if you were to drop this mass when it's at equilibrium, the energy of the system changes, which blows my mind that it depends where you put it. I mean, I think that's really cool. But it turns out here, okay, the energy of the system doesn't actually change, because when it's compressed, what type of energy is there? Okay, when this is compressed, all the energy is tied up as elastic potential energy. Okay, 1/2 kx squared. Well, just by putting another mass on here, did you change the spring constant? No. And if you do it right at the instant of maximum compression, you haven't changed how much it's compressed. So the energy shouldn't change. No extra energy is added. So all energy at this point is elastic potential energy, which again is 1/2 kx squared. So adding this mass does not change the total energy of the system, which is interesting. Okay? And as the spring decompresses, all that energy is still staying the same. But now, as it decompresses and this starts to move up, as spring decompresses, and the elastic potential energy turns to kinetic energy? Well, let's think about it. What's the equation for kinetic energy? 1/2 mv squared. We just increased m. So now, the speed, if m has increased, and k, the maximum k hasn't changed, we haven't added or taken away any energy to the system, if m has gone up, v cannot be as big. Okay? The velocity or the speed cannot be as high. M has increased, V must decrease. And what we mean is the velocity at each point will be lower than it was before you put that mass on there. Okay? The speed at equilibrium must have decreased. So I have on my sheet here, the speed at equilibrium must have decreased, but the speed everywhere must have decreased. Okay? It's still moving, just moving more slowly, which is what this suggested. The time increase, which suggests a slower motion, this bears it out. V must decrease at all points as compared to before. Okay, so it's not moving as fast, the period increases. The last thing that I might question is, does the amplitude, does the amount that it moves from equilibrium change? And the answer is no. Dropping the block here did nothing to x. Okay? The energy is still the same. When the energy goes from kinetic energy, when it's back at equilibrium, all the way out and it's at its maximum elongation, the spring is, it will still have as much energy, so it will still go out just as far. So it turns out, even though the period increases and the velocity decreases, the amplitude of oscillation remains the same. Interesting question, tricky question. You really have to understand what we mean by dropping it right onto the mass, and we have to understand the different types of energy at each point in order to answer this question. Okay? This is a tricky question. I remember giving it last year, and it wasn't a very easily answerable question. Okay? I wasn't given full credit to almost anyone on this one. It was kind of tricky, but it is doable. So, this is the end of the tutorial. This is the end of my little video lecture series. I really would like you to, hopefully you've watched all of these. I mean, I think it probably took, I'm going to say less, maybe a little bit more than an hour and a half of your time. In reality, in class, this would probably take us 2 hours to go through because I would be trying to get answers from you guys. So we have saved a little bit of time here, which I'm glad for. I am interested in doing video lessons in the future. Maybe not with you guys, but with the future groups. I want to hear feedback. Okay, I want to hear feedback on, is this useful for you guys? Okay, what can I improve? What can I get better at? What was good already, if anything? Okay, this is the first time you guys have done anything like this, most likely, tried to learn from a video. You will have some chances at this in college, maybe more than I did. I'm not really sure what they're doing in college now. But this it has some nice features because you can go back and watch this whenever you want, or be like, okay, what did he say right there, and go back and find it. I would like to hear some feedback on this, good, bad, otherwise. You can either email me or tell me in person. None of you are shy about telling me things that I do wrong in person. So if you like to do that, I would appreciate comments, nice comments. And by nice, I mean, you know, if it's criticism, please, constructive criticism. Anyways, thank you for watching. I hope you've had a decent enough break without me interrupting it all the time with my video lessons and emails, and I will see you on Monday.